Radial gate used for flood control. Detailed explanation. Radial gates, also known as tainter gates, are curved water control structures commonly used in dams, spillways, and flood control systems. Their primary function is to regulate the flow of water in rivers, canals, and reservoirs. Because of their strength, reliability, and efficiency, radial gates are widely employed for flood control applications. Below is a comprehensive explanation of radial gates, with a focus on their role in managing floods. Structure and design of radial gates. A radial gate consists of the following main components. Curved gate leaf. The gate is curved in the horizontal direction, forming a circular arc typically 90 degrees or less. This curvature distributes water pressure evenly and reduces the bending moment on the structure. Radial arms. These are structural steel members that transfer the hydraulic load from the gate leaf to the trunnion. Trunnion bearings. Fixed pivots or bearings on which the radial arms rotate. These allow the gate to open or close by swinging around a central axis. Hoisting mechanism usually consists of electric motors, chains, ropes, or hydraulic cylinders to raise or lower the gate. Sealing system, rubber or neoprene seals prevent water from leaking past the closed gate. Working principle. Radial gates work on the principle of rotation around a horizontal axis via trunnions. When the gate is lowered, it blocks the flow of water. When it's raised, water is allowed to pass beneath the curved gate leaf. The curved shape helps reduce the amount of force needed to lift the gate and improves operational efficiency. Role in flood control. Radial gates play a critical role in flood management systems by controlling the volume and timing of water releases. Here's HW they help. Controlled water release. During heavy rainfall or upstream flooding, radial gates are opened to release excess water from reservoirs, preventing overtopping of dams and protecting downstream areas. Rapid response. Radial gates can be operated quickly, often remotely via automated systems, making them ideal for emergency flood situations. Flow regulation. They help in regulating river flow during the rainy season, ensuring that downstream floodplains are not inundated suddenly. Spillway integration. Radial gates are often installed in spillways, where they allow excess water to safely bypass the dam structure during high flow events. Urban flood control. In urban areas prone to flash floods, radial gates in diversion channels or stormwater systems help redirect water flow and prevent city flooding. Advantages of radial gates for flood control. High strength and load capacity, suitable for high headwater levels. Low operating force. Curved design requires less energy to operate. Durability. Designed for long service life in harsh conditions. Efficient flow control. Can be finely adjusted for precise regulation. Low maintenance. With proper design, maintenance needs are minimal. Applications in flood control systems. Radial gates are used in various flood control structures. Spillways of dams. Primary flood control application. Barrage gates. Control flow in large river diversion structures. Canal head regulators. Manage water diversion during high inflows. Tidal barriers. Prevent seawater ingress during high tides or storms. Flood diversion channels. Redirect water to safe zones during extreme rainfall. Real-world examples. Neelam Jhelum Hydropower Company Pakistan uses large radial gates on its spillways for flood management. Three Gorges Dam, China, equipped with massive radial gates to control the Yangtze River during floods. Hoover Dam, USA, integrates radial gates in its flood spillway design. Operation and maintenance. Proper operation and maintenance are crucial for ensuring radial gates function effectively during floods. Routine inspections, bearings, arms, and hoist systems are checked for wear and tear. Lubrication. Trunnions and mechanical parts need periodic lubrication. Seal replacement. Damaged seals are replaced to prevent leakage. Hydraulic system checks. In systems using hydraulic hoists, pressure and fluid levels must be maintained. Modern innovations. Modern radial gates now include automated controls, SCADA systems for real-time monitoring and operation, sensor integration, water, level and pressure sensors for intelligent gate operation, remote access, internet-enabled control systems for distant operation, structural health monitoring, use of strain gauges and sensors to predict maintenance needs. Conclusion. Radial gates are a vital component of modern flood control systems due to their robustness, quick response time, and precise control capabilities. Their integration into dams, barrages, and spillways ensures that excess water during extreme weather events can be safely managed, reducing the risk of catastrophic flooding and protecting lives and infrastructure. Automation and control systems SCADA for radial gates. Automation and control systems are integral to modern radial gate operation, especially in large-scale infrastructure projects where precision, reliability, and efficiency are paramount. The integration of supervisory control and data acquisition SCADA systems enhances real-time monitoring, remote control, and automated responses to dynamic hydrological conditions. This section discusses how automation technologies improve gate performance, focusing on SCADA systems, sensors, and control mechanisms. Overview of SCADA systems. SCADA systems are used to monitor and control industrial operations from a central location. In the case of radial gates, SCADA enables operators to manage gates efficiently, even in complex systems such as dams, reservoirs, and flood control facilities. SCADA provides real-time monitoring, visualizes gate position, water levels, flow rates, and other critical parameters. Remote control. Operators can open, close, or adjust gates from anywhere. Alarm and alert systems warns operators of abnormal conditions, like gate malfunctions or rising water levels. Data logging records historical data for maintenance, analysis, and future planning. SCADA systems are typically integrated with a programmable logic controller (PLC), which acts as the intermediary between field devices, sensors, motors, valves, and the central SCADA control room. Key components of SCADA for radial gate operation. SCADA systems consist of several key components that work together to ensure smooth gate operation. Supervisory system, the central software platform that provides the user interface for operators. This is where commands are issued and data is displayed. Remote terminal units (RTUs). These are installed at the gate or near. Hydraulic, electrical equipment. RTUs collect data from sensors and send it back to the SCADA system. Programmable logic controllers (PLCs). PLCs receive data from sensors and execute control commands like gate opening, closing, based on pre-programmed logic. Sensors and actuators include position sensors, load cells, pressure sensors, and hydraulic actuators. These provide real-time data on the gate's position, pressure, and operation status. Human-machine interface (HMI), a graphical interface that allows operators to interact with the SCADA system. It visualizes system data, alarms, and operational statuses. Functions of SCADA in radial gate operations. SCADA systems offer a range of features designed to optimize gate operations, including remote monitoring and control. Operators can monitor and control gates from a remote location, reducing the need for on-site personnel. For large-scale dams, this can be critical during high-risk events like floods. Automatic gate control. In some cases, gates can be automatically operated based on preset conditions such as water levels, rainfall forecasts, or inflow rates. This ensures a fast and efficient response in critical situations. Data collection and analysis. SCADA collects historical data such as gate position, operational cycles, hydraulic pressures, and weather conditions. This data is invaluable for maintenance planning, troubleshooting, and predictive analysis. Alarms and alerts. SCADA systems can be programmed to alert operators if certain thresholds are exceeded, such as excessive leakage, pressure buildup, or equipment malfunction. This is crucial for preventing damage and ensuring safety. Integration with other systems. SCADA can be integrated with weather monitoring systems, flood forecasting models, and emergency response protocols. This integration ensures that gates operate in harmony with other flood control systems, allowing for real-time adjustments based on evolving conditions. Types of SCADA control strategies. Level-based control. The gate opens or closes based on real-time, reservoir or river levels. This strategy is commonly used for flood control and maintaining optimal reservoir levels. Example: if the water level rises above a preset threshold, The gate opens automatically to release water and prevent overtopping. Flow-based control. This strategy adjusts the gate position based on the flow rate needed, downstream or at specific intervals. It's commonly used in irrigation systems or hydropower facilities. Example: when the required flow rate for irrigation increases, the SCADA system opens the gate to release the necessary amount of water. Time-based control. The gate opens or closes at specific intervals. This is often used for non-emergency applications, where water release can be scheduled in advance. Example: a gate might open every day at 6 a.m. to release water for agricultural purposes. Flood-based control. SCADA systems can detect emergency flood conditions via sensors and weather forecasting, and automatically open gates in response to rising water levels to mitigate flooding. Example: in anticipation of a flood, the system can initiate automatic gate opening as soon as floodwaters exceed a certain prediction level. Communication protocols in SCADA systems. SCADA systems rely on several communication protocols to transmit data between remote units, controllers, and the central control room. These include Modbus, a widely used communication protocol for industrial applications. It allows data exchange between PLCs and SCADA systems. DNP3 Distributed Network Protocol, communication standard used primarily in utilities for secure and efficient data transfer. ETHERNET-IP, a high-speed protocol for transmitting large volumes of data between devices. Profibus, Profinet, used in automation systems for seamless integration with field devices and sensors. The choice of protocol depends on factors like the distance between units, real-time performance requirements, and cybersecurity considerations.